Welcome to the Char Chit Chat, a podcast exploring all things biochar related, coming to you from a small sheep and tree farm in the deep south of New Zealand. G'day. For this podcast, I've decided to do a reading of an article called Biochar Benefits Composting in 10 Plus Ways. This is an article that I was paid to create by Biochar Network New Zealand. It is on their website, and for those of you who do not want to go to the website and spend the time reading it and prefer to listen to content, I'm going to read it out so that you can listen to it through the podcast app and in your own time when you're probably doing something else. Okay, so I'll get right into it. It starts with, what is biochar? Biochar is made during a process called pyrolysis, where the volatiles are combusted and the remaining material left behind is high in carbon. Biochar can be made from any biomass, and it's preferable if this is a waste of some sort. The resulting porous matrix of solid carbon is stable and durable at timescales exceeding hundreds to thousands of years. It has multiple benefits as a soil amendment, and so is fundamentally a permanent improvement in human scale timeframes. Pyrolysis methods. This can be as simple as a pit or trench in the ground to sophisticated and often automated machines. A pit in the ground can be dug with a spade in a location near the biomass. It could be quite small, round in shape, or could be quite long and narrow, kind of like a bath shape dug into the ground. In between the simple pit kiln, there are various form factors of kilns and retorts. The kon-tiki kiln is a well documented and makes around 1,000 litres in an afternoon. Basically, you make a fire in the bottom and then you keep adding branches. And when the top layer of the biomass begins to grey with ash, it is then time to add the next fuel layer. This blocks the air to the lower layers and allows them to char completely. Another type of kiln is called the ring of fire, and it is made from sheets of metal that are bolted together. Imagine these sheets fitting inside a station wagon, being pulled out and then bolted together into like a big circle. It's got a diameter about 2.3 meters across, and you can actually use a machine to load branches and biomass materials into it. And again, the same technique. Make a fire, get it going, start adding branches, and as the flames start to die down and it ashes over a little bit, then you add more biomass. It actually has an outer shield as well, and that helps insulate the fire inside and makes it a more efficient burn, as well as being a safety consideration so that people working near it actually can sort of bump or touch the side and not get instantly burnt. Then we have a mobile retort, which can be used as a batch process. That means you need to fill up the vessel with biomass, and then it's got an inner container, and then you fill the biomass around that container. And when you burn the biomass around the container, it's heating it up and the gases come out and they get burnt as well. Okay, so retort is basically a container with holes in it. Put the biomass in it, you make a fire and cook it basically from the outside, and then the gases come out and they burn, and they kind of help contribute some heat to the whole process. And again, this could be as small as a Milo tin in your wood stove to something that fits onto a tandem axle trailer, quite large. The next section is on residence time and highest treatment temperature. Both of these are critically important characteristics of pyrolysis. In general, highest treatment temperature of 450 degrees centigrade is the minimum required to achieve the formation of linked ring structures at the molecular level. This makes it recalcitrant, which means that it is very stable and long-lived in the soil. And if you can get your highest treatment temperature around 600 degrees centigrade, this is a good benchmark for greatest potential aromaticity and porosity, i.e. your surface area is huge. Temperatures in excess of 750 degrees start to produce diminishing returns as the graphene structures begin to fuse into plates and collapse the internal surface area. So therefore, if you make your biochar too cool or too hot, there's disadvantages. Okay, so we're really going between 600 and 750 degrees. Feedstock form factor is another consideration that will be at least partially dictated by the type of pyrolysis employed. Most continuous process equipment requires incoming material to be chipped or shredded to achieve an optimum average particle size and density factor. Batch retorts can be more tolerant of greater length and diameter pieces, but will need longer highest treatment temperature time at the higher temperatures. That's so that larger wood will still get properly cooked. Feedstock preparation. For general biochar creation, the most favorable feedstocks are those woody materials that are high in lignin and can include things like forestry slash and debris, sawdust, bark, offcuts, and residuals from timber milling, prunings and cullings from horticulture and viticulture, and woody branches and brushy material in the municipal solid waste stream, otherwise known as green organics. These produce a biochar with high surface area and high carbon levels, and these attributes make it highly prized for soil amendment, environmental management, and water quality. Non-woody components of waste streams are best left for input into the composting process, as their resultant biochar properties are lower in stable carbon and higher in mineral or ash content. Quality control. Cross-contamination of feedstock has its risks. Treated lumber and painted wood contain heavy metals such as cadmium and lead, and these pose the highest risk to human health and to environment harm. Burning these can lead to off-gassing and escape to the atmosphere of volatile compounds, including arsenic, and the resulting biochar could have an unacceptably high level of toxic products bound up in its structure. Biomass contamination with chemical compounds containing chlorine or fluorine can also lead to the formation of toxicants. It is interesting to note that small amounts of non-chlorinated hydrocarbons, such as oil or plastics, at levels less than 2% by dry weight do not pose a hazard, as the high heat of pyrolysis causes complete thermal decomposition of the polymers. For commercial biochar production, regular sampling and testing to ascertain the quality of biochar being produced is important. These tests verify that it is within acceptable limits for substances of concern. The International Biochar Initiative publishes assessment categories and protocols for biochar producers. Now we get into 10 beneficial attributes of biochar for composting. Biochar is an ideal input into composting systems because of many benefits to the system itself. An outline of a number of positive benefits that enhance the efficiency and product yield, as well as mitigating some of the negative environmental effects that arise in commercial composting operations, follows shortly. The addition of biochar at rates from 2% to 10% weight by weight can lead to improvements in the following areas. Number 1, water retention. Biochar's sponge-like structure can hold considerable quantities of water. Typical ranges for softwood biochar range from 3 to 4 times by weight to achieve saturation. This characteristic not only helps to maintain moisture levels in the compost, but can also help buffer excess water infiltration during rainfall events and prevent leaching and runoff, and is also a moderating agent helping maintain optimal moisture levels for microbial activity. Number 2, aeration. Biochar does not decay under microbial activity, and the porosity and high internal surface area, as much as 1 hectare per 25 grams of biochar, provides air exchange at the micro scale. This quality helps maintain better aerobic conditions during the composting process, potentially reducing the number of passes required to aerate windrows. Number 3, nutrient adsorption. Cation exchange capacity of biochar means that nutrient ions in solution are attracted and held by it. This means losing substantially less gaseous nitrogen during composting, thus improving the carbon to nitrogen ratio of the finished product. Number 4, pH regulation. Biochar is typically alkaline, often around 9, and so its addition reduces the acidity in composting processes. Presence of calcium, potassium, and other metallic elements makes biochar an effective liming agent. Number 5, microbial habitat. The combination of better aeration, nutrient adsorption, water retention, and pH moderation leads to an environment that is highly beneficial to the microbiology required to create an effective composting process. The carbon matrix of biochar and compost is rapidly colonized by bacteria and fungi, and this home and reservoir keep the decomposition process going better than if they were not there, and for the whole compost process. Number 6, minimize leaching. The nutrient holding ability and water holding functionality of biochar mean that nutrient leaching from the compost pile or windrow is reduced significantly. However, for times of high rainfall, the deployment of biochar in sediment traps as a filter will catch nutrients from the runoff that can then be returned to another compost batch once the sorption limit is reached. Number 7, greenhouse gas emissions reduction. Nitrous oxide and methane have heating potential of about 300 times and 30 times that of carbon dioxide respectively, and under certain conditions both are formed during composting. When biochar has been added, it favors facultative bacteria that prevent or reduce the formation of anaerobic pockets within a compost pile windrow, and thus the formation of methane and nitrous oxide. Number 8, carbon credits and carbon sequestration. Producers of biochar are able to claim carbon credits on the international voluntary markets because biochar is recognized as an effective means of storing carbon safely for long time scales, 100 plus or 1000 plus years. These markets offer accreditation based on criteria that include feedstock sourcing, life cycle assessment of the production and application methods, and quality assurance testing of the biochar itself. The income from these carbon offset and removal credits improve the business case for making biochar as a compost input. The long-term non-decay of carbon in biochar has also led to its designation by the IPCC as one of only a handful of viable and scalable carbon drawdown and removal technologies. Estimates of its potential to reduce atmospheric carbon are by as much as 15% of annual emissions worldwide. Every application of biochar containing compost to the soil thus benefits the climate in taking carbon out of the carbon cycle. Number 9, market differentiation. Biochar enhanced compost sets it apart from competitors and can be promoted on the basis of its increased benefits to soil and plant life, as well as the environmental benefits accrued during the compost making process itself. Number 10, air quality. Strong-smelling ammonia and hydrogen sulfide are significantly reduced when biochar is an input to the composting process. These objectionable odors and potential health hazards are often an issue for neighboring land use and make gaining or keeping consent more difficult. The future? The benefits of biochar as a co-composting addition to compost inputs are numerous and compelling. Imagine a future when a pyrolysis kiln or machine is a standard part of any commercial composting operation. Compost creation is more environmentally friendly, with the carbon sequestered in the end-user soil application, leaving it permanently improved for future generations, as well as being a positive action mitigating climate change. If you'd like further information, we have listed on the website article some great supporting resources that we have found. There is a United States Biochar Initiative brochure on composting with biochar, which is the PDF. There's an awesome video featuring biochar made at a composting facility in Spain, about 4.5 minutes. There's a thorough and referenced blog post on a website called compostmagazine.com. And there's an extremely well-referenced white paper by Pacific Biochar, also in the US, and there's a PDF that's available to go and have a look at. Now, the important thing is, out of all those 10 benefits that I gave, there's 1 or 2 academic references to each one, and there's footnotes. So when you go to the website and read through the article, you can actually go and see where the information has come from. We haven't just made this up. It is supported with academic research and academic papers. This article was really designed for those in the composting industry, but we think it applies to anyone making compost at any scale. All right, so if you're just making it in an urban environment and you have a little compost set up somewhere in your backyard, if you're adding 2 to 10% biochar as you're layering up your green and brown layers, put some biochar in there as you go along, and you're going to get these 10 different co-composting benefits. Then, of course, if you're a larger commercial operation and you can make biochar on a larger scale or buy it in, then you get these other benefits. Okay, I will summarize them again really quickly. Number 1, water retention. Number 2 was aeration. Then nutrient absorption. Then pH regulation. Microbial habitat. Minimizing leaching. The greenhouse gas emissions reduction. Carbon credits and carbon sequestration. And market differentiation. That's really for commercial people. And then improving the air quality. All right, there you go. Thank you for listening. Go to the BNNZ website to find that article and to follow the links and so on. Please share it around. We think that this is really beneficial information, and we'd like to see way more people putting biochar into their compost every time. Thank you. Goodbye.